Hello, Namaste. Welcome to this channel, Chemistry Made Easy by Dr. Ashok Mulik. We were discussing this ionic bonding and structure. Today we will discuss the point of interest, that is dipole moment. So dipole moment can be considered for a bond and for the molecule. So we will see what is the dipole moment. We are representing the bond generally as A plus and B minus, delta minus. So here the bond, that is the electron pair shared between this, is shown in this way, that is dash form. So when the bond pair is slightly moving towards B from A, it produces delta minus charge and this delta plus charge, that is electron deficient center and electron rich center. So this acts as a vector. So in such case, we have seen that the electronegativity values of A are given as XA and that for B are given as XB. So from this we can find that when XA minus XB is equal to 0, then we say the molecule is homonuclear diatomic. When this value XA minus XB is equal to small, then it shows that the molecule is covalent, the covalent molecule. And when this value, that is XA minus XB, is equal to large, then we say that the molecule is ionic in nature. So these values shows that the three different characters, that is homonuclear, diatomic, the molecule may be covalent, the molecule may be ionic. Then depending upon these nature, that is whether it is covalent or ionic or homonuclear. In case of homonuclear diatomic molecule, there is no question of any dipole moment. The dipole moment is subjected only for or applied only for the charge difference, that is XA minus XB, if it is small or if it is large. Then if we see for the bond, the dipole moment is calculated using this mu equal to Q into L. Here Q is charge on atoms and L is bond distance. So this gives us the dipole moment value for say bond AB, or it can be, this is generalized, we can in this way calculate the bond moment for any diatomic molecule or diatomic, that is bond. So here we find that the magnitude of this dipole moment depends upon the electronegativity values of A and B. So greater the value of this difference of electronegativities, greater is the dipole moment of the bond or molecule. And depending upon this, when the value of dipole moment is larger, the ionic characters are more. Now we will see the dipole moment when the molecule is diatomic. The molecules are one is diatomic, another is polyatomic. Then in case of diatomic molecule, this dipole moment for the bond is equal to mu for molecule. The dipole moment for the bond is same for the bond for the molecule. So the dipole moment of the bond and dipole moment of the molecule is same. But when the molecule is polyatomic, means when there are the two or more bonds and atoms more than two, then this mu for bonds are different for each bond. And when the molecule is polyatomic, the spatial arrangement of various atoms, that is structure of the molecule, varies, and depending upon these structures, the net dipole moment of the molecule is also different. And this vector quantity, we know that dipole moment is a vector quantity. So these vector quantities are maybe while calculating the dipole moment for molecule may be added or may be subtracted from each other, and this will result in the net dipole moment of the molecule. In case of, say, the molecule like CO2, when we consider the molecule as CO2, the structure of the molecule is like this. So in this structure you find that this molecule is linear, that is the bond angle is 180 degree. So the dipole moment or the vector is, that is but the dipole moment is pointing in this direction, and the dipole moment of another CO bond is pointing opposite to that direction. So dipole moment of this is cancelled mutually. So dipole moment of this one bond, that is we say mu1, and this is mu2. The mu1 is equal to mu2. So these two are equal. So the dipole moment of both bonds are mutually cancelled, and therefore net dipole moment of this molecule is 0. So we can find this another examples of different molecules. So we will take first the molecule, that is, so we consider NH3 molecule. In this molecule we find that the structure of this molecule is tetrahedral. This is a lone pair, and these are NH bond pairs, that is tetrahedral structure is shown in this way. Now you can show the vectors in this way. So in this structure we find that the dipole moment of this lone pair is pointing in one direction, and other dipoles are also pointing in nearly the same direction but not exactly. So these are adding to each other to some extent, and as a result this bond mu, that is molecular dipole, is consider, or it is found to be 1.47 D. So if we compare this value with another example, that is H2O, so we can have another molecule, that is H2. So in this case, the dipoles are so this dipole is pointing towards oxygen, and the two lone pairs are also having dipole moment in nearly the same direction. So that all these dipole moments are adding to each other. So the net or resulting dipole moment of the molecule is 1.84. New value is 1.84 D. So you will find that in this case the lone pair is 1, in this case lone pairs are 2. So because of this, the resulting or net dipole moment of the molecule is, compared to this value is higher. Now we will consider third molecule, that is NF3. Third molecule is NF3. So the structure of this NF3 is similar to NH3. The lone pair shows dipole moment in this direction, while the bond pairs of NF bonds are showing the dipole moment in opposite directions. So dipole moment of this lone pair is cancelled by or reduced by, means there is subtraction with each other, and as a result of this, the net dipole moment of this molecule is 0.23 D. The net dipole moment of this NF3 is 0.23 D. So this shows that the dipole moments are of the individual bonds are different, and they are, when these dipole moments are working, that is vectors are working in opposite direction to each other, they will show reduction in net dipole moment of the molecule. Now we will see that the molecular dipoles are obtained by, or as they found that they are experimentally obtained. These are not easy to be calculated by usual methods which are suitable for diatomic molecules. In case of polyatomic molecules, it is difficult to calculate the net dipole moment of the molecule. So it is generally obtained from experimental values, and it shows that the experimental values are most important, and we can compare the calculated values of the molecules. So we can consider the molecules like, say, chloromethanes. For example, we can find these molecules like CH3, or we will take first the CHCl3, then CH2Cl2, and then CH3Cl. So here we will find that the experimental values, experimental D and calculated D. So these are from vector and from PC spark method. So we find that, so these are two values. So experimental values for CHCl3 shows that there are 3 CCl bonds which are polar. So the value is much higher, it is 1.87. In case of CH2Cl2, there are 2 CCl bonds. So their values are relatively smaller, that is 1.60. Then in this case there is only one CCl bond. So the dipole moment is 1.01, that is much less. The calculated values from vector shows that much deviation, that is 1.77 for CHCl3. Then the value is much higher for, that is 2.08 for CH2Cl2. Again in case of CHCl3 the value is CH3Cl, the value is again 1.82. So these are not much comparable. Again according to PC Spalter, values are 1.51, 1.50, and in this case the value is relatively comparable, that is 1.16. So these values are showing that the calculated values are not directly matching with the experimental values. So in this calculation, the values used are mu for CH bond, mu, that is dipole moment of CH bond used is 1.3, and that is mu for CCl bond is much higher, 4.9 into 10 raised to minus 30D, that is Cl. So these values are different, and these are usually in the calculation for these methods. So with this we will stop here and we will see next point in the next lecture. Till then, goodbye, see you next time. Please keep watching this video and sharing it with your friends. Please press the like button and bell icon button. Thank you very much.